There's pleasure to welcome Alba. We'll talk about better parton showers for hadronic collisions.
Good morning, everybody. Yes, as Conrad was saying, we are going to switch gears a little bit to vacuum physics, but since the homework by the organizer was to give a theoretical overview of vacuum parton showers, an approach to extend them to immediate showers, I have tried to do this in the talk, so it's a little bit speculative, but I hope it triggers discussion. And the whole talk is organized like a little bit of the ingredients that you need to build a parton shower, and a discussion, for example, whether you need to do 1 to 2 splittings or 2 to 3 splittings, what the advantage of having a dipole shower, whether the evolution variable and how do you redistribute momenta make a difference. And the most important point for me is point number 2, that a parton shower is a collection of ingredients that gives you an event record at the end, but actually there is a way to formally gauge the accuracy of your parton shower in the language of analytic resummation, as I will show you in a minute. So this has been established very recently for vacuum physics, and I think we should try to move in that direction for in-medium parton showers. Of course, we know that it's a little bit more complicated, but I would have a proposal on how to do this. And I would like to do a little review on where do we stand for the in-medium parton showers. So as I said, everything is vacuum, but I will have some notes about the in-medium physics. So let's start at the beginning, like why does a parton shower actually works? And it's because of the structure of QCD is extremely kind to us, and the matrix element for having an n+1 system actually can be written as the matrix element for having n particles times some additional factor that contains the infrared divergence of your matrix element. And more concretely, if we are dealing with a system of n particles, I should do it with the pointer, with a system of n particles, and then we have an additional radiation, if this emission is collinear, meaning that the angle with I is very small, the matrix element just factorizes at what you had before times the splitting function and the propagator of this particle. And in the soft limit, what we recover is the iconal form factor. So that's why you can do the iteration of this kind of structure as a Markovian process. So each emission is independent of each other, and you can treat the n+1 system as what you had before times a new factor. And what Fabio presented yesterday would be the in-medium analog of this collinear limit of the matrix element. Are emissions completely independent from each other? Well, not completely. For example, if we take the case of a soft gluon emission, the matrix element for generating this soft gluon emission is the iconal factor that we all know that if you integrate over the azimuthal angle of this pk, actually you get a condition on the angle of this emission. It cannot be whatever, but it has to lie down in the cone opened by the dipole that is splitting, and this is what we know as color coherence. And this is what we know that in the medium is not the same property, but actually you have this decoherence factor and the anti-angular ordering condition that was derived many years ago by Conrad, Yassin, and Carlos. So emissions are not completely independent, and the main property that one needs to take into account for writing a parton shower is this angular ordering constraint. And there are two ways of incorporating the fact that whenever you have a soft gluon, you need to take into account this theta function. One is just directly do an angular order shower. And since you are doing an angular order shower, it's going to be a 1 to 2 splittings. In order to ensure energy momentum conservation, you need to, every time you split, you need to redistribute the momenta in all the particles of your event. And this is what Herwig does in Monte Carlo. But we already know from theory that these type of showers are limited. They cannot be next to leading log accurate, as I will explain in a minute. So there is an alternative approach that is to write a dipole shower. That is what Pythia, Sherpa, and the new shower in the game that is called Panscale is doing. So what is a dipole shower, and why does it automatically account for this angular ordering condition, even if they are not ordered in angle? So the shower can be transverse momentum order, for example. So how does a dipole shower work? In E plus E minus collisions, we have a set that splits into a QQ bar, and this QQ bar system emits a gluon. So this is viewed in a dipole shower and the large NC limit. This gluon is considered to be this dipole down here. So we go from a one dipole system to a 2 dipole systems, and the color indicates the color connections of the particle. So the gluon has a 3 and a 3 bar end, and it connects to the quark and the Q bar. And now, how do you write this in a shower language. So you will say that the probability of going from this system to this other system is written first as a phase space integration over the kinematics of the emission that you are generated times the splitting probability. And now, what is this splitting probability? You automatically identified here the Altarelli-Parisi splitting function for one of the legs. So the probability that this K is collinear to I, and then the probability of this emission is just the splitting function plus the probability that this K is actually collinear to the other leg of the dipole, and you would have to apply the splitting function from this other leg. And if you are writing the dipole shower as a sum of two collinear showers, how do you recover the soft limit properly? And for that, the key ingredient is this G function that automatically distributes the soft divergence into the I and the J legs. So this is a function of the rapidity of the emission. And when the rapidity of the emission, let's say, is positive, let's attribute to the quark is in the positive rapidity. So when the rapidity of the emission is positive, then it will give a largest weight to this term down here, while if the rapidity is negative, so more collinear to the anti-quark, this function automatically weights more this term. So by this weighting or this interpolation, the dipole showers automatically get the collinear limit right, because when the emission is collinear to one of them, you just recover the Altarelli-Parisi splitting function, but you also get the soft limit right, because you are distributing in between the I and the J legs. And yeah, so this is what I just said, that in a singular behavior, you can show that this splitting probability reduces correctly to the soft limit and correctly to the Altarelli-Parisi splitting function in the collinear limit. This was E plus E minus. What happens when you go to hadron collisions, that you don't have just one type of dipole, but you have multiple dipoles. Imagine that we start from a QQ-bar system that you are going to produce a set boson, for example, an X. After an evolution step, you can radiate from your initial state legs. So now these guys are coming from the proton, so you are going to have a radiation from here. So this would be an initial dipole, because both your particles are in the initial state, and you are evolving backwards, right? After a second evolution step, you can either emit from the final leg or from the initial state leg. So you will have initial final emissions or final initial emissions, and finally, you can also have final emissions. That is when all your legs are already in the final state. So you need to take into account all the evolution of these four dipoles when you go to hadronic collisions. And for the moment, we are making a shower that only considers color singlet production. So in the hard system that you are producing is color singlet. So you don't have to take into account emissions that can come from your initial partons and from your hard system. And I will explain why this is a problem, but in principle for this audience, what you need is a shower that can do dijets, or at least a Z plus jet or gamma plus jet. But at the moment, we are at the level of just Drell-Yan process. And the second ingredient that you need to take into account when you go to hadron colliders is that you need to add the PDFs into the splitting probability. So the splitting probability stays the same, plus the fact that every time that you emit, your X fraction is going to change. So you need to add one element for one of the partons, one PDF ratio for one of the partons, and the other for the other incoming guy. So the first question is, are we actually taking into account this initial state radiation in heavy ions? Yes, and how? So based on a formation time argument, you can say that initial state radiation happens way earlier before the medium is formed. So in principle, you shouldn't quench these emissions, but of course, through this initial state evolution, you are generated final state emissions. And these final state emissions can in principle later interact with the medium. So how is this done in basically all jet quenching Monte Carlos? Is that you generate all this initial state radiation with PIFIA using nuclear PDFs. So in this ratio, instead of having a PDF, you have a nuclear PDF. And now these final state radiations are quenched, depending on the model, how they do it. This initial state radiation is particularly relevant when you have an azimuthal correlation, because it can change the balance in the PT between your set and your jet. For example, when you go to very forward rapidities, or when your jet radius is very large, because then if your radius is very large, it can happen that the emissions that end up in your cone are actually coming from the initial state and not from the final state, so radiation coming from the jets. And this has just recently started to be explored, like what's the role of this initial state radiation by Corina in her talk at Quark Matter. So okay, we have we know more or less how to calculate the splitting probability of a hadron collider dipole shower. What are the degrees of freedom that we have? The first one is what is our evolution variable. That can be KT, angle, as I will explain in a little bit. The second one is how do you redistribute the momentum? Every time that you emit, how do you redistribute that momentum? And the third one is how do you define the angle of the emission? So this is very important because this is going to tell you whether you attribute the emission to be more collinear to one leg or to the other. So the definition of this eta bar, that is the angle of this emission, defined in some way, as I will explain you in a bit, is also very important. And these 3 degrees of freedom actually have a direct consequence in the accuracy of your shower. So now comes the question, how do you define the accuracy of your shower? And there are 2 possible ways of doing this. And I would like to emphasize that this is a relatively new paradigm on how to establish the logarithmic accuracy of a shower. The first thing is to realize that the shower, as I started at the beginning, has to reproduce the matrix element, the exact matrix element in certain limits. So we know that if we generate a soft emission, that is what I'm drawing here, is the Lund plane for emissions, so KT on the y-axis, rapidity on the x-axis, and I'm putting here an emission in the bulk of the Lund plane that is soft and is not collinear. So we know that the matrix element for this emission has the typical double logarithmic enhancement. So if we run a shower just for one emission, it should reduce to this matrix element. If we go one step further and we generate 2 emissions and the second emission happens at a commensurate KT, still the 2 of them very well separated in rapidity, the first emission, these 2 are completely independent, and the correct matrix element is just the product of the independent matrix elements of the 2 emissions. And this, since we are doing the second emission at a commensurate KT, we lose a logarithm. So this is not double logarithmic accuracy anymore, but this is already single logarithmic accuracy. So the first thing that we need to check in our shower is that if we generate 2 emissions, one of them at a commensurate KT, but very far in rapidity, the second emission shouldn't modify the first one. So the matrix element should be the product of the 2 emissions independently. So this is one way of testing your shower, just truncating it at a very few emissions level. The other way is to realize that what the shower is doing numerically is to actually resum all the logarithms that you have that are generated because of the fact that you have 2 complete distinct scales in your problem, the Hart scale and the hadronization scale. So we know that we can calculate analytically the logarithmic structure of a lot of observables in the literature. And this, the resummation structure of these observables take the form that I have here, where in principle the key variable is the logarithm of the 2 disparate scales that you have, that is this L, and the second variable is alpha S, so the coupling. And the expansion is written as the leading log that goes like 1 over alpha S. Next to leading log just loses 1 power of alpha S with respect to the leading log. So it only depends on alpha S log. And the next to leading log has an extra power of alpha S. So I would like to emphasize that this term here, so reaching next to leading logarithmic accuracy in a shower is nothing crazy, but it's actually taking into account all terms that are order 1. So this is the minimum that you can do in order to do something predictive. Now, how do you test if your shower is actually next to leading log or not? Imagine that you just take the ratio. So you just take your shower, run it, compute an observable, and take the ratio to the next to leading log analytic prediction. And you see, this is the ratio here for a given observable, that is this y23, well, whatever. And you see that the ratio is different from 1. Now you can ask the question, is this because my shower is not next to leading log, or because the shower in principle generates spurious terms at higher orders? How am I sure that I am isolating the next to leading log contribution only? And the trick is, given that the resummation structure works like this, if you keep alpha S times the logarithm fixed and take alpha S to 0, then automatically you are killing all the higher order contributions. So what you see here is different values of alpha S, then make an extrapolation of alpha S to 0, and you see that there is still a deviation from the next to leading log result. So by doing this limit, automatically you are sure that the shower, in this case Pythia, is not next to leading log. Can we do this? Hey, what happened? There was things here. Okay. So what happens when you try to do this for a medium? Can we do this for a medium-induced shower? So in vacuum, we know now how to do it. In the medium, what do? I write it in the blackboard. No. Well, what I'm gonna say is that in the medium, in principle, we know that the medium-induced shower is generating terms like alpha s time the length of the medium divided by the formation time of your emission. So this is the parameter that the medium-induced shower is resounding. No, let's see. No way. Okay. Sorry? Yeah, I don't know. Well, so this is the parameter that the shower is trying to resound. Maybe I can discuss it later. Anyway, I can discuss it later. Maybe we can discuss, because then for the Zoom people it's gonna be impossible. But well, I think with the recent developments by Conrad and company and Adam and Johannes, there is also a way on how to define the medium-induced shower, the accuracy of a medium-induced shower. But anyway, so we know how to establish the accuracy of a parton shower in vacuum. We can do this fixed order test or this all order test. And the rest of this talk is to present the first next to leading log shower for color singlet production in hadron collisions that was presented in this paper, and there is another one coming right away. So in order to evaluate what is the current state of the art, we coded a shower that is a proxy for what is in Pythia, in Sherpa, and yeah, actually that's it, in Pythia and in Sherpa. So how does the shower inside Pythia work? Will they generate the evolution variable is a transverse momentum, and then for the recoil, they have a mixture between, depending on the dipole type that you have, you can either do a local recoil, so the transverse momentum is conserved at the level of the dipole, or do a global recoil where you redistribute the momentum. And the key point here is that they define this angle of the emission in the dipole rest frame. And you will see that this has a direct consequence on the logarithmic accuracy of the shower. So how I'm gonna test this? As I said, I'm gonna do a fixed order test first, when I'm gonna generate one emission with the shower, that is this gluon down here that I put as a dot in my KT and rapidity plane, and then generate a second gluon that can be emitted from any of the dipoles that I have. So it can be from either of these four combinations. And what I'm gonna check is that if these two gluons are very far away in rapidity, as I said, the first gluon shouldn't, the kinematics of the first gluon shouldn't be altered by the emission of the second gluon. So the condition that we want is the KT of the first gluon before and after the emission of two stays the same. And this is equivalent to say that in the color coherence picture that we have, that the first gluon kinematics can only be affected if your second emission lies within the cone of your first gluon. If my second emission happens completely far away in rapidity, why should this guy care? So what I plot here is the ratio of the KT of this gluon pre and post branching, and what I'm coloring in gray is the region that is not relevant for next to leading log, because what I'm saying is correct in the limit in which these two emissions are far in rapidity. So when the two emissions are nearby, in principle, we can expect that the kinematics are modified. So what we see is that if I emit from the initial final dipoles, I recover a ratio that is equal to 1, so that's good. When I emit from the final initial dipole, I see that the KT of my emission is modified even if my second emission happens 10 units in rapidity far away. So the first gluon is taking the recoil after the second emission is emitted, while it shouldn't, because it shouldn't know that this second emission happened. Why is this happening? This is because of the definition of rapidity. So what you would expect now in the Lund plane is that your gluon recoils only when the second emission is in the vicinity, and that the quark and the anti-quark take the recoil anywhere else. But due to the definition of rapidity of these showers, they are wrongly attributing the recoil in a region of phase space that, in principle, should be the quark or the anti-quark. So when you define the rapidity in the dipole frame, and then you boost to the event frame, what you are causing is that the cone that I was talking about before is gigantic, because you are not defining the rapidity in the way you should. So this is the first thing that one is to fix. You cannot define this dipole partitioning in the dipole frame. because otherwise you generate the wrong transverse recoil assignment and you are not next to leading lock. If you go to the all order test, you can compute, for example, the ZPT spectrum and do this ratio that I was telling you before in the alpha is to 0 limit, and you see that the current showers have a deviation of up to like 35% from the next to leading lock expectation. And this PT set, for example, is fundamental for any W mass extraction that is now like very hot topic. The second thing that we can look, for example, is the azimuthal angle between the leading jets. Again, the mistake is gigantic, like up to 80%. And in heavy ion, this is particularly relevant because if you are not describing the azimuthal structure of your event properly, you can generate, well, it's important to identify like rich-like structures in high multiplicity PP events. So the conclusion is dipole KT is not an next to leading lock shower. And how do we fix these problems? Well, we have two solutions. In fact, one is called pan-local, meaning that the recoil is distributed at the level of the dipole. And the first thing that we do is change the definition of rapidity. So rapidity should actually be defined in the event rest frame. The second thing that we do is to change the evolution variable. So instead of being a KT, we add an angular dependent piece with a beta exponent that is a free parameter. And beta can be something between 0 and 1. So if we set it to 0, we recover a KT order shower. And if we put it to 1, it will be a time order shower, as I will explain in a little bit. If you do the recoil locally with a transverse momentum order shower, you are screwed, you are not next to leading lock. As I can explain, since I am running out of time, I can explain this a little bit later, but essentially you need a positive beta in order to be next to leading lock accurate. The second shower that we propose is called pan-global, and in this case, the momentum is distributed along the event. And in this case, we can do a beta equals 0 shower, so it can be transverse momentum order, but it cannot be time order. So we have seen that when we take beta equal 1, we generate a mistake because you see the same ratio as before. When the second emission happens at a larger value of eta, we introduce an spurious mistake in the momentum. So time order shower is not next to leading lock. We understand why, and we think we know how to fix it. But at least there are two showers that work. So pan-global with transverse momentum order shower, you see that if I repeat the same exercise of seeing how the KT of my first emission changes, this automatically generates the correct next to leading lock pattern. Pan-local the same. As I said, you don't have to worry about this behavior because it's in when they are close. So this to be next to leading lock. And the all order test, we tested a bunch of observables. That is what you see here on the y-axis, and the points are red if you are far away from the next to leading lock expectation. So these are the showers in Pythia. These are the new Panscale showers, and they all lie within the next to leading lock result. So we conclude that we have at least 1, 2, 3, 4 showers that are next to leading lock accurate for color singlet production. So what do you do with this in heavy ions? Well, the first thing is to have a Panscale shower that is able to do digets, so that your hard system is a diget, and we can do it at leading NC. At full NC, because everything that I presented was at full color. At full NC is a little bit more complicated. So imagine that we solve the digets. How I envision that this can be incorporated into a Monte Carlo, and I use JetMed because I'm more familiar with the physics, would be I start from my hard system. I do my initial state evolution and the final state emissions. Now the vacuum emissions. Now for the final state emissions, I need to take into account that the phase space is not the whole plane, but I have a constraint on my phase space. Now we have finished all the vacuum-like emissions up to the medium boundary. From these sources that I created, now I can generate the medium-induced shower. And there are at least two possibilities. Either I do it, how is it done nowadays? So with a rate for the set component and broadening for the angular component, or I could develop a medium-induced dipole shower. This is not there yet. But in principle, we could have a dipole evolution also in the medium. Now, once we have reached the medium frontier, we have to pass again the list of particles to Panscale to do the out of medium cascade. If you don't do a dipole shower, so a dipole shower knows about the color connections in between the particles. If now you switch to a 1-to-2 shower, you lost this information, but well, maybe we don't care. And then the fourth step, that is what I couldn't explain, is how to compare the shower with analytic calculations and establish the accuracy of the showers that we have. That is something that we didn't pay attention so far, and I think we should do now, because we know what is the matrix element in the soft limit and in the collinear limit, at least. So we should be able to run our showers and see if we reproduce the expected limits. And I'm done, so thanks. Thank you very much.
Thank you so much, Alba. I didn't mean to just stop you at the moment, but I guess it's a nice point to start a discussion. So first to you.
I think essentially you're talking about the effect of global, momentum conservation, because it's a recall. Essentially, it's global momentum conservation, and that is probably, I understand, if you only talk about like either initial parton shower or final parton shower, but do you actually consider there's this effect between initial and final state parton shower?
Yeah. I mean, we do it everything concurrently.
And in that case, do you think that's probably better approached by matching? I mean, I know people doing matching next leading order metrics with parton shower. That is probably better approach by that of
no. It's complementary, because right now what we have is you generate the matrix element. In this case, it would be QQ bar to a set boson leading order matrix element, and now the QQ bar evolve backwards, and they generate and the final state emissions generated by the QQ bar evolve forwards until the end. But now we can do digest. So then from the digest system, the first emission that you generate, you can do it with the exact matrix element, and then from the system you run the shower. So with a next to leading order calculation, you cannot reproduce the full phase space of the shower, right? So the first emission is the fixed order part that you generate with the correct matrix element that next to leading order, next to, or whatever you want.
Yes.
And from that system, you run the shower.
Yeah, but now you're talking about the the final state shower that you have recall is somehow have some kind of feedback from your initial state radiation. That's what you're saying.
Yeah, but I mean, this can be done. Like the initial, you fix first, you generate the matrix element. So the hard system that you are generating, and from there you generate initial and final state radiation. So in the end, what you have is a next to leading order plus next to leading log shower. And energy momentum conservation doesn't destroy the accuracy. If you do it properly, doesn't destroy the accuracy.
So we have time for more questions. Yeah, Yassine?
Yeah, just a quick question. So do you have an idea of how large are the next to leading log contributions compared to the?
Yeah, because like when we run the showers, not in the asymptotic limit to test next to leading log, but in regular conditions, we see differences between pan global and pan local, for example. So this indicates how big the next to leading log spurious terms are. Well, spurious, I mean, uncontrolled, because we know that we don't, and the difference in between these two depends on the observable, but it can be up to 10-20%. It's sizable, yeah.
You have a question from James?
Thanks. I have a very basic or naive question. Back when one of your slides, when you're introducing the parton showers and writing this, n+1 to n relation, are there arguments or reasons to think on that very basic level whether that will hold in a medium case, these kind of simple relations, or whether even that would break? I mean, I guess, you have, the n+1 matrix element and basically the product of the splitting function and the n particle matrix element. Do you think, or have people thought whether that structure should hold for some arguments and you should modify that splitting function, or whether that structure can be anything?
Maybe our chair can say something, but I think that at least in the soft limit, so when you start from a vacuum like dipole, again, this was like a vacuum like splitting, and you generate a medium-induced emission, what they showed that you can still write it as the matrix element times a correction factor. So in the soft limit, no, I think that this still holds this what I showed here. Yeah, here, this thing. Yeah. So instead of, yeah, at least here you can write something similar with instead of having just the iconal. Well, you have the iconal, but the medium modified iconal. And in the collinear limit, I think what Fabio was showing yesterday is gonna be similar. So you can also do this. So in principle, I think the idea would be, but I didn't thought this through completely. But for a medium-induced shower, I think that you can replace this splitting function by what Fabio was computing, what Fabio and collaborator were computing, and then you need to be sure that you reproduce the soft limit correctly. And this in vacuum, we know how to do it. In the medium, I think that we can try to do it. And then, no.
In the medium, we have also some other scales. So I guess that's where the very, very soft and very, very collinear limits are kind of again controlled, but there are also some intermediate regimes.
Yes,
It
yes.
should be very interesting to look at.
Yeah.
So any questions from Zoom or here in the audience? We are a bit over time, but no? Okay, so let's thank Alba for the talk and Philip.